Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the nature of matter itself. What is the matter with matter? Matter is that stuff that makes up the universe. In fact, let's even make a more interesting definition for matter. Matter has mass, and as mass, it must be pushed around by forces. So anything that can accelerate a mass through a force is how matter interacts with other matter. Kind of a weird way of thinking about it, but that's old Newton's laws. So we just go all the way back to Newton's laws and say, there's some stuff that we'll call matter, and matter may be accelerated or decelerated, and the thing that does that accelerating or deceleration is called a force. And so there are 4 different ways the universe has of pushing things around, and they're called the 4 fundamental forces of nature. One of them is gravity, and gravity obviously attracts every mass, attracts every other mass, and causes it to accelerate. That's the nature of gravity. Well, we know by Einstein now, and just Newton's laws work very well, but we know Einstein's version of gravity says that matter curves space-time and it falls inside of that curved space-time. But what we can think about, let's go back to Newton's laws, Newton's version of gravity. We have 2 pieces of matter that then gravitate to each other and they accelerate towards each other. That's what we really care about, is the acceleration of matter. Well, what's the other thing? Well, we could put a pair of charges on top of them. We could have a plus charge and a minus charge, or an electric charge. And they can, if they're the same type of charge, they repel. If they have the opposites, then they'll attract each other. And that will cause the matter to accelerate. The electromagnetic force causes an acceleration. And the thing that we call the electromagnetic force, that which transmits the force. In the case of gravity, it's the curvature of space-time. But with the electromagnetic force, it's the transmission of light, photons, back and forth between the charged particles. As they move and vibrate, they change the electric field. And that vibrating, moving electric field then indicates how that thing should be pushed or pulled by the charges that as the light is receiving them. All right, so the electromagnetic force is another way that matter can be accelerated or moved. And the next one is the strong and weak nuclear forces. The strong nuclear force holds protons together inside of the nucleus of an atom and holds neutrons and protons all inside a nucleus, as well as holding the constituent quarks of an atom. But we'll talk about that shortly. So the strong and weak nuclear forces only really come into play when we talk about nuclear particles, or the centers of atoms. All right, so what do we mean by matter? All right, so I just said it's the thing that gets pushed around when their force is acted upon it. All right, so you have to have some way of interacting. Well, gravity says that if it's got mass, you have something to do with the gravitational force. If it also has charge, then the mass that has the charge will then be accelerated. If it interacts via the weak nuclear force, by the exchange of W or Z bosons, or it interacts by the strong nuclear force, the interchange of gluons, then the matter then will accelerate because of these interactions. Well, what makes up matter? Well, matter in the universe comes in from very big things to very small things. And we'll start with the tiniest, like quarks and leptons, which are fundamental particles. You can't break them apart any further. And there's subatomic particles like protons and neutrons, which are composed of quarks. And then you think about electrons, which are fundamental particles themselves. The fundamental particle called a lepton is an electron, and it can't be broken apart. And then you can take protons and neutrons and put them together, and you get a nucleus of an atom. And if you put some electrons around it, you've got an atom. If you put atoms together next to each other, then you've got molecules. If you have huge molecules, you can have a buckyball or a bucky chain or a carbon nanotube, or you can have a crystal of iron or a nice little quartz crystal of amethyst or something. Or you can have deoxyribonucleic acid or just water, H2O. Many of these things, complex molecules and simple molecules. And then you can take all sorts of molecules and pump them together, make crystals out of them, or make agglomerations of them, put some over here and some over there, and pack them together, and you might get a person, or an elephant, or a giraffe, or a car, or a planet, or a star, or a galaxy. You know, all sorts of stuff you can make out of atoms. And just think of atoms as your building blocks of everything, and that's what you can make it out of. So ordinary matter in the universe is what we call atoms, and it makes up all the stuff that we know. So what's an atom? All right, so an atom has a nucleus, and a nucleus has some electrons swarming around it. And that cartoon thing that we always see and always have seen for a long time, that's a really helpful visualization, but it really doesn't look like that. And we'll talk about what we mean by that next time, but we'll look at it, but we'll kind of go with this cartoon for a little bit. And the cartoon says that in the center of the atom, there is a nucleus, and the nucleus is composed of protons and neutrons. And the neutrons are uncharged and electrically neutral. They don't do anything. They're a little bit more massive than the proton, but the neutron itself just a tiny bit more massive than the proton, but the proton has a positive charge. So the proton's positive charge is part of the nucleus, and the neutron's positive charge can be in the nucleus, and they're surrounded by a cloud of electrons. And if it's a neutral atom, then there's one electron for every proton that exists in the atom. So you got 1 and 1. If it's ionized, then there will be fewer electrons than there are protons. And you can also have ions where there are more electrons. That's kind of weird. You'd have to have a very strange arrangement so the electrons don't fully screen the protons, or it might be a dense environment where the electrons are being forced upon the atom. But in general, we can think of that electrons and protons come 1-to-1 with respect to each other. And when they go 1-to-1, we see a cloud of electrons and we have a neutral atom. What's funny is also that we talked about fundamental particles. So an electron is a fundamental particle and a proton is not. It is a subatomic particle. It's composed of quarks, but a proton is about 1,800 times the mass of an electron. And if we think about how much mass that is, a typical person, college students, say here at William Paterson, the typical student is about, if they're eating ramen on a Saturday night as they're studying for their finals, then they'll be like 140 or 150 pounds because they're losing weight and they're all stressed out. So, but now you take 1,800 of those, and that's approximately 100 tons. So an electron, let's say a normal person, is the mass of an electron. Then the mass of the proton would be 100 tons. I'm just trying to think of what exactly would be 100 tons. I mean, dump trucks, huge dump trucks. Well, we'd have to look at earth mover dump trucks, those enormous things that are in mining operations or strip mining operations. Those are hundreds of tons. So there's some big things that are hundreds of tons. And we can think about, wow, me compared to 100 tons. And so some pickup trucks, or some large trucks that you might go buy, are about a ton. So 100 pickup trucks or 100 SUVs or 100 large cars and compact them together and call that one object is the mass of one thing, the mass of the proton compared to, say, you, if you are an electron. Kind of interesting. All right. So now how are they distributed in space? According to this cartoon, it makes it look like, oh, everybody's all happy and joyful, and the electrons are really big, and the protons are really big, and the neutrons are really big. But they're not. They're incredibly tiny. The typical size scale of an atom is on the order of 10 to the minus 10th meters, so about an angstrom or so. And most of the atom itself is empty space. In fact, only 1 part in 10 to the 15th of an atom is actually taken up by the matter of the atom. The rest is the fields of electromagnetism between the electron and the proton, the disturbed field that actually keeps the electron in place, and the protons, it tells the electrons where they are. In any event, this is really interesting because we think, well, how empty is it? If we were to say, take a relatively decent sized building or a house, and a typical house might be, say, 30 meters across. Specifically, if we go to the Museum of Natural History, we see the Hayden sphere is exactly 30 meters across, that big glassed-in ball at the Hayden Planetarium in New York City, so at the Museum of Natural History. In fact, there's a really fun exhibit in there that shows the size of a proton compared to the atom. And in fact, the 30-meter wide, which is 100 feet wide, 100 foot wide ball, compared is, say, the size of an atom. Somewhere in the surface of that ball is where the electron is for hydrogen. Let's call it just plain old hydrogen atom, which only has 1 proton and 1 electron. So if we're looking at that, a typical atom of hydrogen will have 1 proton and 1 electron. The electron is somewhere on the surface of that ball, and the proton is at the center of that ball. How big is the proton? It's about a 6-point font of a 6-point printed font. So it's the size of a mote of dust. So that's how small the proton is. It is a mote of dust compared to something 100 feet in diameter. That's amazing. So most of all atoms is completely empty space. Electrons are really tiny. Electrons are about 100 times smaller than a proton in terms of size, which is fascinating. So an electron is a tiny, 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 tiny thing. And even still, the mote of dust compared to where the electron is on the surface of an atom. Anyway, so how do we distinguish atoms? Well, we can have multiple protons in the nucleus. So let's say we have multiple protons, and these protons tend to be, well, they're always at the nucleus, but if you have one proton, we call it hydrogen. If you have two, we call it helium. Three, we call it lithium. Four, we call it beryllium. And then nitrogen, carbon, oxygen, and so on. The name of the element tells you how many protons it has in it. And so the atomic number is the number of protons. And every single atom, every single element, which is chemically distinct and operates, and each of the chemistry is different between each one. So right now we know that there are 118 elements that have been made. About 24 of them have to actually be made in laboratories, and they only live for like microseconds or nanoseconds before they fall apart. About 87 of them are metals, meaning they have the capacity to allow electrons to flow off of them they're valence electrons, so they can easily be stripped off. 11 of them in naturally, well, like normal human circumstances, not too hot, not too cold, good enough for a human, not too high in the atmosphere, not too far below the ground, that 11 of them come as gases. 2 of them occur as liquids, like mercury is one of them and bromine's another. A bunch of them are radioactive, about 25 or so. And these are the chemical elements, and only the most massive ones are only formed in particle accelerators. So when we look at the name, we've seen periodic tables in the past, so let's look at how we read the name of the elements. Always the number of protons, the atomic number, describes the name of the element. And so if it's got 1 proton, it's always hydrogen. If it's got 23 protons, it's always vanadium. If it's got 19 protons, it's always potassium. If it's got 11, it's always sodium. If it's got 2, it's always helium. If it's got 6, it's always carbon. That's the name of it. And so all of the names are exactly what the atomic number is. Now the funny thing is that the names themselves then become abbreviated. So hydrogen is H, beryllium is Be, lithium is Li, sodium of course is Na, gold is of course Au, oh my goodness, potassium is K. What's going on here? So basically, most of them are abbreviations, but some of them derive from Greek and Latin, so we don't necessarily have a one-to-one with their abbreviations and the names that are common in say, English, but they would be common in other languages. So, but the name is always, no matter what language they're spoken in, the name of the thing describes the total number of protons. And so there's a whole slog of them, and the periodic table of elements is broken up into similar chemical behavior, such as hydrogen and lithium and sodium readily give away their electron, and fluorine, chlorine, bromine, and iodine readily grab an electron, and so they're not filled electron shells, so they will take an electron. So the most reactive elements come on both sides of the periodic table. So that's kind of how they go. And the farthest right ones are the noble gases, and they hardly react to anything because their electron shells are filled. So when the most abundant elements out of all of the elements in the universe, almost 75% of all the matter, all the elements of the universe, all the matter of the universe is hydrogen. And 25% of the matter in the universe is helium. And then oxygen, carbon, neon, nitrogen, silicon, iron, magnesium, and sulfur come next. And so all of the things beyond hydrogen and helium make up only about 1% of all the matter in the universe. So if we want to say, what is the matter of the universe? It's hydrogen and it's helium. That's pretty much it. All the other stuff, the things that we're made out of, everything else that we encounter that's made out of, that's just really rare stuff. And some of it's really rare compared to the rarity of it is. So hydrogen and helium is everything in the universe. And where's the helium on Earth? Well, it's embedded inside of natural gas deposits, and it comes to us as a result of emissions by the sun. All right, so remember we talked about the total number of protons to give with the atomic number, but remember we also said that neutrons can be in the core, in the nucleus of an atom. So when neutrons are in the nucleus of an atom, if they're differing numbers, we call them isotopes. So the isotope, meaning isotopic, meaning the topos is the number of protons. And so the number of protons is always the same. So hydrogen, plain old hydrogen, has none, no neutrons. But if it has a neutron, it's called deuterium. And there's deuterium when it has two objects in the core. And it's called tritium if it is hydrogen with two neutrons attached to it in the nucleus. So tritium, though, is radioactive and will readily decay. That neutron will readily decay away. But in every case, to make an atom with deuterium, it only takes, even though there's two things in the nucleus, there's only one electron because the proton has one charge and the neutron has no charge. So if we look at something a little bit bigger, say carbon, carbon-12 has 6 neutrons and 6 protons, carbon-13 has 6 protons and 7 neutrons, carbon-14 has 6 protons and 8 neutrons, and once you get too many neutrons, it tends to fall apart. So isotopes with lots and lots and lots of neutrons tend to fall apart. And if they happen to have fewer neutrons than protons, they'll also fall apart too. So radioactive carbon is very familiar. We call it radioactive carbon dating, and carbon falls apart. And what does falling apart mean? We mean that it's radioactive. And radioactivity is a decay of a subatomic particle from one type of thing to another. So tritium, as I said, was radioactive. Tritium will spontaneously decay at some random interval. A random atom, a random nucleus of tritium will spontaneously, one of the neutrons will go, I don't think I want to be a neutron anymore, and turn into a proton. And in so doing, the nucleus will spit out an electron and also spit out a neutrino, and those things will go away. But now it's helium because there's 2 protons and 1 neutron. So it's light helium. So that's what we call light helium, see, it's got 1 neutron less than the number of protons. That's light helium. And likewise, carbon-14 decays to nitrogen-14 by one of the neutrons transforming itself into a proton. And so carbon, which has 6 protons, becomes nitrogen, which has 7. So now we have 7 and 7, and the nitrogen is happy. And in so decaying and switching from a neutron to a proton, an electron gets sput out and a neutrino gets sput out. And if a neutron is also all by itself, it'll spontaneously decay in about 11 minutes or so. So these neutrons really don't know how to stay together because the proton and electron really want to fly apart. And the thing that's holding them together is the weak nuclear force. And that's the reaction. If you have a neutrino coming out, you've got the weak nuclear forces, which we talked about in the earlier part. So these things are all called beta decays. You can also have an alpha decay where a full helium nucleus of 2 protons and 2 neutrons gets spat out by a very massive nucleus like uranium or something like that. You can also have gamma decay, where the nucleus itself is in an energized state and emits a very high energy light particle, a very high energy photon in the form of a gamma ray. So wait a second, that's where we get the gamma ray idea from. Is gamma rays are high energy light. So we have alpha, beta, and gammas. Alpha particles are heavy nuclei, beta particles are electrons, and gamma particles are photons of very high energy. And these things were given their names during the early years of studying radioactivity back in the turn of the 19th century, right around the turn of the 20th century in that area. So people named them that way, and sometimes you'll always be hearing alpha particles or alpha decay or alpha this. That always means a helium nucleus. And we can say beta decay or beta particles, and those are always electrons. And the gamma rays, what we know about gamma rays, they're light, and that's where that comes from. So why we care about all this is because when we're looking at astronomy, we can't actually reach out to the stars and take a bucket of a distant star and bring it home and see what's cooking in there. We can't do that. So we want to learn what is going on at those distant stars and what's happening to the matter over there. We wish to identify what kind of matter it is. And that's where we get Kirchhoff's laws of spectroscopy, because every single element on the periodic table has its own spectrum when it gets excited or gets collided into and emits light. If it'll absorb specific light energy, and it'll emit those things at exactly those wavelengths. So every single chemical element in existence has its own individual spectrum, And those spectra are always the same no matter what, because every hydrogen atom is exactly the same in the entire universe. Every carbon atom is the same in the entire universe. Different isotopes, but they're the same. They're always the same because because protons are the same everywhere in the universe, and neutrons are the same everywhere in the universe, and electrons are the same everywhere in the universe. So every atom is just like any other atom if it's the same isotope. And even if they're different isotopes, they're almost the same because they just differ by the total number of neutrons. And there's no difference between them other than the number of neutrons. But what's a neutron? What's a proton? What's an electron? They're the same things everywhere in the universe. And you stack them together to make atoms, and each individual atom and all the molecules associated with them. Well, let's stick with atoms because we're talking about elements for a second. The atomic elements, each one of them has their own individual spectral signature, and that can be discovered. In fact, it was first discovered that these things existed as objects spectroscopically, because we'd have to say, oh, what do we have in this gas? If we have some rarefied gas that we cannot see, but yet it glows because of the energy we're putting into it. If it glows with that characteristic pink, it must be hydrogen. If it glows in a particular different way, it's helium. And we break apart the spectrum and we look at the spectrum of the thing as it's glowing. Or maybe it's cool and we've got something behind it that's hot that passes through the cool gas. The absorption lines are exactly the same as the emission lines, and that's what we talked about with Kirchhoff's laws of spectroscopy. So every single element, every single atom is the same in the cosmos in terms of what they are, meaning one carbon-12 atom is exactly the same as every other carbon-12 atom in the universe. And they all have exactly the same spectral fingerprint. That fundamental statement that the spectra of all of these are identical says that the light interacts with the matter, interacts with carbon-12. No matter how it interacts, all light interacts with everything. And that is part of an incredibly important idea called the Copernican principle, which means the cosmological principle says that there is no special place in the cosmos and that all laws of physics are the same everywhere. And we will rely on that idea to get us out to the stars and learn what is out there. But what's funny is that this whole thing that I discussed about the nature of these things, it's not been known forever. So let's see next time how the history of the atom developed through time. See you soon.